Okay, welcome back. So let's continue with our discussion. So actually remember, so we discussed some applications, right? So let's see another application. Actually, idea is the same. Somehow we are going to use polynomials to approximate some bad functions actually to certain values evaluated in terms of a complicated function. So over here, we have something like this. This is our function. And near x equals a, we try to use Taylor polynomial of order 2. So what does it mean? Of course, we should remember how can you construct the Taylor polynomial. So Taylor polynomial is a very specific polynomial um, for which coefficients can be determined by using derivatives of f itself at the point 8. So remember, so the corresponding Taylor polynomial uh, generated by f at centered at x equals 8 is of the form like this. So n starting from 0, a n x minus 8 to the n, and that's all. Where, so very special, here is the magic actually. So ans are determined by using higher order derivatives of f evaluated at the point a, n factorial. So here is the very important point. Be careful. I didn't write this series is equal to f. This is not true in general. This is just some other series generated by f, not necessarily converges to f. So this is important. But there are special cases we will see later. There is a nice theory about this. If you already know that f has a certain convergent polynomial series, then you can equate them. But in general, if you write something like this is wrong. Okay, so don't do this. So this is something else. So now we just build a new series by using certain information coming from f itself. Okay, so but we need, we just want what we want, just a second order Taylor polynomial. So we don't need this polynomial, involving infinitely many terms. Just consider at most degree 2 polynomials. So we want a Taylor polynomial of degree 2. Okay, so what does it mean? That is, we really want to compute the following polynomial. So since you have a degree 2 polynomial, you have, for instance, constant term. This is exactly when n equals 0, plus the first order term. You see, degree of x is 1, and the second order term. So degree 2 terms are contributed from here. Okay. Okay, so that's it. This is the second order term basically. As you said, so that's all. We just want that much polynomial. At most degree 2. So we try to approximate the value of f by using this polynomial. This is the idea. Okay. And actually, of course, we need coefficients, right? So we need those coefficients, and we know how to compute them. So the algorithm actually here, right? So this one. So we just use this algorithm to compute those coefficients. So where a0 is just f of 8 itself. So if you compute f of 8, we know the functions is at what was it? Cube root x. And what else? For instance, a1. A1 can be computed like this. First derivative evaluated at 8 divided by 1 factorial, which is 1. And so what is it? So remember, so f is square root, third root x, and 1/3 here, x to the minus, okay, something like this, evaluated at 8. Okay, you just compute the value. So I may have sometimes numerical mistakes, but just check. And what is a2? A2 will be a double prime. So we have 2 factorial here. And then if you compute in a very similar way, so let me write it down, the results. So 9 times 32. Okay, it's not the exact result, but anyway. So you have something like this. So you know the coefficients, you know the polynomial. So let's try to approximate. So hence we get something like this. We try to approximate the value of, the function f approximated by this polynomial, right? Px. And this is just, okay, 2. So let me write it down. Minus, okay, something like this, x minus 8, minus 1 times 9 times, okay, 32, x minus 8 squared. And that much, approximately. So we just use that much information to approximate the value of f. So we just estimate f of 10. Remember, that was the question, right? F of 10. So where is it? F of 10. So we really want to approximate this thing. So estimate f of 10, which is just, we defined as a function. So something like this. And by using this approximation, this is just, okay, this is approximately 2 times, okay, this times 2. Just put x equals 10. So that's all. Minus, okay, 9 times 32 times 4. I guess correct. And then that's all. So we try to use that much information to conclude that, okay, this thing is approximately, so just compute the value here. I don't know if you compute just just check the numerical result. I guess something like this much number. Okay, and this actually can be using a Taylor polynomial, of degree 2. Okay, so that much information. So approximately you have this. Okay, this kind of numerical results. Okay, fine. This is actually how, as I said, your calculators, basically calculators use that kind of algorithm. So it depends on your accuracy. So what kind of sensitivity you need. For instance, degree 2, using degree 2 polynomials, maybe it's not that much sensitive you like. Maybe you need more sensitivity, therefore you need to use more polynomials of degree high. You need to use higher degrees as well. Then you will have more resolution if you like. Okay, fine. So that's all. Okay, next one. So next application. So let's try to use again Taylor's and the Maclaurin series. So what kind of application we have? Okay, so in this case, a kind of a limit problem, and by using series representation, we can deal with this kind of limit problems. If you look at carefully, as x approaches to 0, you have 0 over 0 type indeterminacy. Remember, what a standard student do, just use L'Hopital rule, but we are not going to do this. We use something else. Okay, let's see. solution. Uh, of course, in the question, assume that because the value is 0, you cannot compute the value 0. This is not defined at 0, but you can check the limit. Therefore, we need to compute limit x approaches to 0, this function cosine x minus 1 plus x squared over 2 minus x4, something like this, and the denominator we have x to the 6. So let's see, let's look at this limits. But as I said, we try to use power series representation. So we should recall the following. So recall the power series representation of cosine x. Remember, cosine x is just given like this. So n starts from 0 to infinity, minus 1 to the n, and even terms, right? So even powered terms, basically, to n factorial. Therefore, you have a power series like this. X squared 2 factorial plus so what is it? So 1, 2, so 4 factorial minus x to the 6 factorial plus, it goes like this. Okay, fine. So let's use it. So we know this is true for all x. For all x, this equality holds for all x. This equality holds for all x. Therefore, it's nice. So let's use it. So just observe the following. And so we have the following observation. So limit x approaches to 0, f of x, just use those series here, and let's use it. Instead of cosine, let me just write down the couple of terms. I mean, we have this infinite series, right? So x to the 4, just compute this, x to the 6 factorial, and it goes like this. You have an infinite series here, and minus the other terms, plus x squared over 2 minus x to the 4, because these are given. And actually, we almost done, divided by, what is it? X to the 6. So if you look at carefully, there is, this one, these are cancel out each other. And similar here, this term, and this term, and that term. Okay? And let's see what we have. What we have, limits x approaches to 0. Actually, the first term, first degree, you may see here x to the 6. So let's take the parenthesis of x to the 6. So why not? X to the 6. What is the first term? Then minus 1 over 6 factorial. Remember, the next term is plus x to the 8. Therefore, now we have plus x to the 2, 8 factorial, minus x to the 4, 10 factorial, and story goes like this. Okay, and we don't have another terms, and that's all. Right? Can you follow? Okay, fine. So now we have another cancellation. Right? This term and this term cancel out each other, and let's see what we have. As x goes to infinity, as x goes to 0, as x goes to 0, maybe I should specify like this, x approaches to 0 here. Look at those terms. Look at those terms. Here, those terms are all involves x. So as x approaches to 0, those terms here approaches to 0, right? So because they involve x, and this part approaches to 0. Therefore, what you get as x approaches to 0 minus 1 over 6 factorial. Okay. So fine. So that's all. We compute the limit. And actually, since f is continuous, I mean, since we want f to be continuous, so where is it? Remember, assume that the value f0 is chosen so that f of x is continuous. So find f of 0. Therefore, due to the continuity, due to the continuity, so what does it tell us? F of 0 is exactly, by definition, limit x approaches to 0, f of x, and this is 1 minus 6 factorial. This is f of 0. So we compute f of 0. What about part B? Part B is, I guess, a little bit tricky. So let's see what we have. So in part B, we really want to find fourth order derivative of f evaluated at the point 0. Okay, fine. So part B. So let's see. So we already have a power series representation for f, right? And remember, maybe I should write it down. By using part A, so from part A, or using the same analysis that we did in part A, so after canceling this x to the 6 terms, f of x is given by minus 1 over 6 factorial and plus, what was it, x squared divided by 8 factorial minus x to the 4 divided by 10 factorial, for instance, and the plus, let me write it down, a couple of terms. 12 factorial, and story goes like this, dot, dot, dot. Okay. After those cancellation, before taking the limit, we have this actually, right? And okay, minus and dots, dots, dots. And actually, this is a kind of a power series, right? And we know that this is true for all x. Remember, it involved cosine. So let me write it down as a series, right? Like this. So let me use this dummy indices k. So let me denote by bk here, the coefficients. And if you look at carefully, we have just even terms. I mean, the even powered terms. So x to the 2k. And we have some bk. So we have a kind of a convergent series representation. I mean, i.e. f of x has a convergent power series representation. Fs, okay. Oops. Okay, so let me continue. So what we have, so where were we? So, okay, so we have a power series representation. So f itself has already a power series representation. So this is a powerful result. And therefore, by Taylor theorem, so by Taylor theorem, so it says that actually when you write down the corresponding Taylor series generated by f, it is indeed convergent and it converges to f. So this is the crucial part. You should understand. So by Taylor theorem, it says that its Taylor series, I mean the generated by f converges converges to itself. But remember, this is important property of this f. Since it has already a power series representation, what I mean is that f of x indeed convergent. This is not the case. This is where amazing thing happens, actually. This is not the case. This is n starting from 0. Okay, you know this a centered at 0, n factorial times x minus 0. So it's just x, if you like, n. Okay, so let me denote this coefficients by an. So this is not the case in general. Okay, and therefore let me write it down carefully. And so on the left hand side you have a series representation like this, remember. So let me write it down once more. 8 factorial, okay, x squared, okay, minus 1, okay, 10 factorial, x to the 4. So what was the next term? Plus 1, 12 factorial, x to the 6, minus, okay, it goes like this. So this is actually f. We already know this information. Thanks to this theorem, it tells us that on the right-hand side, you can write down everything like this. an, x to the n. So here, an's are f to the nth 0 divided by n factor. So this is amazing. This is not true in general. So this is important. Okay? This part is important. Not true in general. And, oops, not that part. Okay, this part is important and this part is important. Okay? And then we want, what we want, remember, we look for f to the 4 evaluated at 0. But actually this is from right-hand side. From right-hand side, this is just, what is it? This is just 4 factorial times a4. By definition, this is from right-hand side. And then, actually, this is the coefficient of the term of degree 4. So need to look at degree 4 term. Okay, so a4 is a coefficient of the term of degree 4 on the right-hand side. So just look at degree 4 term, the coefficients of degree 4 term on the left-hand side. And here is the coefficient you are looking for. Right? This one. This is degree 4. And therefore, actually, what does it tell us? So actually, look at left-hand side. It tells you that basically a4 is equal to, remember, this is just b0, this is just b1, this is just really, okay, anyway, so these are, I don't know why this happens all the time. So b4 is exactly corresponds to b2 because these are exactly the coefficients of the term of degree 4. Right? And we are done. So therefore, so f fourth order derivative is equal to 4 factorial times what is b2 is just 1 over 10 factorial. Okay, this is just minus divided by 10 factorial. Okay, that's all. Okay, fine. So be careful how to compare left-hand side and the right-hand side. Okay, next problem. Okay, what is it? Okay, this is again a similar kind of problem. We are not going to use L'Hopital rule, of course. It's really hard to use L'Hopital rule. Maybe if you try use L'Hopital rule, you will end up with a kind of an infinite loop. So you cannot get any meaningful conclusion by using L'Hopital rule again and again. So therefore, we use Taylor series representations. And as before, we should recall, and use. So using the following series representation, for instance, series representation for sine x. So we should remember this. So what was it? So we have odd powers, basically, x to the 2n plus 1 divided by 2n plus 1 factorial. This is sine x. What else we need? We need, for instance, cosine x. And this is just a derivative of the first expression, actually, on the above. Minus 1 to the n, x to the 2n divided by 2n factorial. And what else we need? Exponential. So the exponent. So these are, remember, these are valid for all x. Okay. And exponential n starting from 0, x to the n factorial for all x. So we are going to use them. Actually, we are going to use the versions of them. Instead of, for instance, x here, instead of x, we need 3x, of course. Instead of 2x, we replace by 2x. Instead of x, we replace everything by x cubed. But we know how to do this kind of reorganization business. We get used to it. And so let's use it. So why don't we use this kind of approach? So we have limit x approaches to 0. So let me write it down, the whole expression. So sin 3x, okay, multiply by minus cosine 2x and divided by e to the x cubed minus 1. So let me write it down everything. So let me write it down infinite series. And let me write down a couple of terms. First couple of terms. For instance, sine 3x. If you substitute 3x instead of x, here is what you have in the first couple of places. So something like this, divided by 3 factorial plus 3 to the 5, x to the 5 factorial, and goes like this. First couple of terms, if you like. What else? The other one, 1 minus, so let me write it down by multiply everything by a minus sign. So 1 plus 2 squared x squared 2 factorial minus 2 to the 4 x to the 4 and the 4 factorial and the plus 2 to the 6 x to the 6 and the 6 factorial and minus, and it goes like this. Okay, I hope you follow. Oops, maybe I should. Where is it? Okay. Okay, it goes like this. So you have another infinite series here. And in the denominator, let me write it down. First couple of terms. Here, 1 plus, okay, x cubed plus x cubed squared. Therefore, we have x to the 6, 2 factorial plus x to the 9, okay, 3 factorial, and the story goes like this. And of course, with parentheses, minus 1. Okay, let's try to analyze this ugly term here. So here what we have, okay, these are cancel out. There are some cancellations. These are cancel out each other. And if you look at carefully, so we are going to just multiply term by term. So you have polynomials, just multiply them term by term. But of course, it's impossible to multiply everything because we have infinitely many terms. But let's try to see the pattern. Let's try to understand a couple of terms. And actually, if you multiply this term with this one, what you get? You have something x to the 3, degree 3 term. So what if you multiply this thing by that one? You have something degree 4. So you have something degree 3, you have something degree 4. And what if you multiply this term with the next one? You have something degree, oh, is this 4 or 5? Degree 5 and degree 7. And story goes like this. You have at least degree 3 term. And what if you multiply this term? I mean, so it goes like this. So degree getting larger and larger and larger. But at least you have degree 3 and degree 5. What if you multiply the second one? Let me show it like this. Second one with the first one. You have degree 5 polynomial. What if multiply with this second term here, degree 6, I guess. Oops, no, degree 7. And then actually story goes like this. If you look at carefully, you see the pattern. You will see polynomials, infinitely many, but consist of at least degree 5. So here is what I mean. So let me write it down something like this. So this is equal to limits x approaches to 0. Actually, we have the first term here, 6x cubed, and plus the others, other part consists of polynomials at least degree 5. The way of writing this in a very compact way is the following. So the following notation. This is called the big O notation. Big O notation, x to the 5. Okay? So meaning of this notation, these are consists of polynomials of degree at least 5. Okay, this is our notation. It's a compact notation. And divided by, if you look at carefully and take the parenthesis of x cubed, let's see what we have. We have something 1 plus, okay, x cubed, 2 factorial, and dot, dot, dot. And if you look at carefully, so these are cancel out each other if you do the cancellation. Let's see what we have. So the limit as x approaches to 0, so cancel this thing, x plus. So all terms here consist of at least x to the power 5. And you cancel out by x to the power 3, which means that least possible degree you will see is x to the 2. And divided by 1 plus x cubed, 2 factorial, and the plus, maybe the next term if you like, 3 factorial. All others involves x actually. And here the previous trick, as you see, as x approaches to 0, this part approaches to 0, all terms over here consist of x. Therefore, all approaches to 0 as x approaches to 0. Therefore, the result would be 6. Okay? This is the idea. Of course, these are vanishing. I don't know why these, my writings are disappearing. I don't know why. It's really weird. I mean, never see this kind of technical problem before. Okay, magic. So I just correct them. Okay, so the next problem. Let's see. This one. So actually, we did this before, kind of a problem. So we really want to understand those higher derivatives. I mean, it's really hard to find. I mean, how can you find them? Actually, we will use Taylor theorem as before. Remember, the most important observation is f itself is already given as a power series. It has a convergent power series. So the most important observation, So observe that f has already a power series, convergent power series representation with this radius of convergent in this interval, -1, 5, 5 open. Okay, therefore, for the value x equals 2, we are done. X, actually 2 is in this interval, so we can use it. So by Taylor theorem, Taylor's theorem, in this radius of convergence, we know that f converges to its Taylor series representation. So what is this? Remember, this is a kind of a series generated by and near 2, let me say, because we interested the values here, the Taylor series expansion near 2, and factorial x, what is it, -2 to the n. Or maybe I should use another letter. Maybe I just use k here, k here, and k here. Okay, k. So in general, this is your Taylor series representation generated by f. But if you have something like this, if has already a power series representation, so it tells you that the f itself, on the right hand side, we have a series like this. Let me write it down. X -2 divided by, what is it? Okay, 2n plus 1 and 3 2n plus 1 is equal to f of x, and this f now converges. This is not the case in general. I just try to warn you. Now this is really converges to the Taylor series generated by f. Okay, ak here, x -2 here to the k, with each ak is determined by the derivatives of f. Okay. As I said, this equality is not true in general. Not true in general. But we are lucky. Now, if you look at carefully, so let me denote this part, or maybe some other color, maybe, I don't know, the blue one. Let me denote this coefficients as Bn, and we have AKs. Remember, we need to be careful. We need to understand where, we need to understand which term and which term we need, which degree we need. And remember, the question is, okay, first of all, okay, the first observation, actually, this derivative term 2 is automatically 0. Why? Since in the left-hand side, right, on the left-hand side, there is no even power, okay? Since on the left-hand side, no even power terms, okay? There is no such term, therefore this automatically 0. We just compare right-hand side and left-hand side, but we should be careful. And the second thing, so the second question was f of, I don't know, f derivative 51 or something like this. This makes sense actually from right-hand side. we automatically see that, I mean, this red part, f of this much derivative evaluated at 2 can be given by 51 factorial times a 51. Okay, so a 51 is exactly the coefficient of which term? X minus 2 to the 51. Therefore, on the left-hand side, now we need to look at the coefficient of uh, x minus 2 to the 51. But on the left-hand side, be careful. Indices are different here. Therefore, on the left-hand side, and on the left-hand side, this corresponds to, okay, we don't touch this term, but on the left-hand side, this is exactly b to the this coefficient, b 25, because we just look at the coefficient of this term on the left-hand side, and actually on the left-hand side, degree 51 is achieved when n equals 25. Okay, so there is a detail here, so we need to be careful. Okay, so indices, there are different algorithms. Actually, in the left-hand side, we need to be careful. So therefore, the coefficient of this power, the coefficient of the term with degree 51 is b25. Okay, maybe I should write it down more detail. Degree 51 achieved when n equals 25. Remember, because 2 times 21 plus 1 is 51. Okay, look at the indices, how we manage degrees here. So be careful. Maybe I should specify like this. Okay. And fine. Therefore, you need to compute this coefficient. Okay, 51 factorial times, let's compute it. This is 1 over, okay, 27 times 3 to the 51. Yeah, I guess that's all. Right, so we are done. Actually, we can reorganize everything if you want. 51 factorial divided by 3 to the 54. So that much derivative evaluated at 2 is just by comparing left-hand side and the right-hand side. Accordingly, we have something like this. Okay, and that's all. Okay, so this is the result basically. And as I said, since there is no even power terms, this thing is automatically 0. Okay, but for odd powers, we need to be careful. This is the idea actually. Okay, fine. Actually, I will stop here. This is, I mean, that's all for this week, or just for this session. And see you next time. And maybe before this, as before, I have, so where is it? Just a second. Okay, so maybe before closing up this session, we have exercises as before. And by using more or less the same ideas, for instance, using power series representation for these functions, right? By using power series representation, you can compute limits as we did before. And similar here, you should find first Taylor or corresponding Maclaurin series, and then probably you will end up with a kind of alternating series and use the estimation theorem as we did in the previous problem. And similarly, here in the third one, now it asks basically the use of Taylor polynomial of degree 4. Remember, we use degree 2 polynomial, I guess. But similar idea, you have some just extra coefficients. That's all. And the last part is okay, is the usage of Taylor theorem, I guess, and it's a kind of a tricky problem. Okay, fine, that's all, and thank you very much, and see you next time. And I will stop here.